is video 5 of what I originally called a 4-video playlist. I realized I didn't answer the specific question that was given in the group study session. So let me do that. Everything I said previous to this is true, and we're going to use that to solve the specific question. And the question that was given was describe the motion of a square wire loop. So in other words, we're assuming that this side along the top or the bottom is the same as S. And if that's the case, what's the equation of motion? Well, it's still this equation up here during that period of time that the loop is entering the magnetic field. Once it's in the magnetic field, the braking stops. There's no more flux change, and so whatever velocity it's achieved at the point where it's completely in the magnetic field, it will continue to be that velocity. And then as it comes out of the magnetic field, the equation above still applies. You just have to change your starting point and your initial velocity. So let me show you what I mean by all this. The upshot of all this is that this square is so small that there's very little magnetic braking. In fact, the velocity goes from 10 meters per second to 9.99 meters per second as it goes into the field, and as it comes out, it's decreases by about the same amount. So essentially, it doesn't decrease at all. The velocity stays the same. Let me show you how we come up with those numbers. Well, first of all, we want to know how long it takes to completely enter the magnetic field. Well, we're going to use this equation here, which describes its motion as it goes into the magnetic field, and we're going to say, for what t does x of t equal s? In other words, how long does it take for this end here to get completely inside the field? And we can figure out what that t is by just solving that equation. So I substitute this x of t here. I get this equation, I solve for t, and the program knows how to do that. So if I I want to put t in the auxiliary slot. I'm going to do that. Let me get in front of the t. I do a control T that puts it in the auxiliary slot, and I say solve for that. And that's the solution as a formula, and as a number, it's that. So it takes about, that's 1/100th of a second for the wire loop to completely enter the magnetic field. I can then compute the velocity at that point in time by just calculating x prime of t, just using the formulas that I developed up here. X prime of t is this number. So it has only gone down to 9.99 meters per second. And let's assume that the magnetic field is exactly s meters wide. That means it'll start coming out immediately. In other words, it'll spend no time in the magnetic field where it's completely in the magnetic field. It starts coming out immediately. In that case, we can just assume that our t satisfies this equation. X of t equals 2 times s. In other words, it's now gone into the field completely and then come out of the field. And we can solve for t in that case in the same way we did before. And again, I'm just going to substitute for the function and let the program do the hard work here, solve for t. And then let's see what that number is. That number is 0.022. So I can put that up here in my t to make my equality correct. That's going to be 0.02002. That's rounded a bit. Okay, so in other words, it takes about 2/100ths of a second for the wire to pass completely through the field. And what is its velocity then? Well, I've changed the t, so now x prime of t represents the velocity as it leaves the field, and that's 9.98 meters per second. So it's only slowed down 0.02 meters per second. Now, if the field were larger than s, then these velocities would be the same. It would enter the field, and once it got in the field, its velocity would have decreased to 9.9 meters per second. Then it would continue along at that velocity as long as it's completely in the field. And as it started coming out, it would slow down that additional 0.01 meters per second. So its velocity as it came out of the field would be 9.98 meters per second. And let's just look at what that looks like. Again, we're going to go back and assume that the magnetic field is exactly S on this side. Its depth is S, the same as the side of the rectangle. If we do that, then this is what the motion looks like. And that's essentially a straight line. It's 10 meters per second almost all the way along. Here's the period where it's coming into the magnetic field. Here's the period where it's coming out. And if you looked at that in greater detail, you'd see a slight change from a straight line. And then once it's out, it's just a straight line. So to get that formula, you have to break up this motion equation up here into two pieces. As it enters, it's just x of t. As it leaves, it's x at the point where it leaves the field plus the derivative plus the velocity at the point where it leaves the field times the time beyond which it leaves the field. So, well, in this case, it essentially ends up as a straight line. But remember, that's only because this r up here is so big. The resistance is so large, there's so little current, so there's so little heat produced, so there's so little breaking of the wire loop. And if we change that resistance to sort of a realistic number for a copper wire, the picture would change to this. If we do a copper wire with a much lower resistance, we would have that the wire loop does stop. In other words, its breaking point is computed to be 1 centimeter, and we're assuming that the side of the wire is 10 centimeters, so it would enter into the field just 1/10 of its length in that case if we had this as our resistance. So again, summing up, if the resistance is very high, then our wire is going to, we're only going to be looking at sort of this little section of the total equation of motion. So it's almost a straight line down here, so you don't get any braking at all. And in terms of the velocity, you're looking at a minuscule little portion up here where there's no change or very little change in the velocity of the wire loop. So that I think that answers the question.